for inviting me. Let's see, I have to push continue here. Thanks for inviting me. I haven't given this precise talk before. I decided to do something a little more general than I'd originally planned because the audience isn't the usual one that I speak before, astronomers instead of engineers. So I may make a few mistakes and miss some things that I meant to talk about, but here we go. Let's see, it doesn't want to go to the next page. Why is that? There we go. Okay, so I'm going to start out by discussing very briefly why optimization is important, and then categorize the different types of interplanetary trajectories, which can be categorized by the difficulty of finding the trajectory solutions. And I'll give you a couple of examples of cases where analytical solutions are actually available. And then we'll talk about the more interesting case where the analytical solution is not possible and we have to use some more sophisticated methods to find trajectories. These are methods that have mostly been developed since about the 1980s. In fact, it pretty much spans by coincidence, kind of spans my career as a researcher. They're frequently called direct solution methods as opposed to calculus of variations methods, which are referred to as indirect methods. Then we'll talk about probably the most exciting area right now in terms of trajectory optimization, which is the use of heuristic methods and evolutionary algorithms. And I'll describe a little bit about what those are and why they, what advantages they have over some of the extant methods. And then I'll talk about some examples of using heuristic and evolutionary algorithms to find optimal trajectories. And then finally, we'll talk about the most challenging problem, but very practical one, of finding optimal outer planet trajectories using gravity assist flybys. That is to say, the kind of trajectory that was used for Galileo and then later Cassini. So why do we need optimization? Well, we need it primarily because our technology with regard to launch vehicles really is not very advanced. Even some of our largest launch vehicles are not really all that capable, especially for outer planet missions. In fact, the only case that I know of where a direct trajectory was used for an outer planet mission was New Horizons to Pluto, but that was a pretty small spacecraft. When you get to a spacecraft like Galileo or Cassini that are as big as an automobile or heavier, the only way to do that with existing launch vehicles is to use gravity assists or flybys. So we need optimization for many reasons. The technology that we have available is not that great. If you can optimize the trajectory, you might be able to use a smaller launch vehicle. And it turns out that roughly speaking, the cost of a launch vehicle is almost linearly proportional to its mass. So when you go from a Delta to an Atlas V to a SpaceX, the heavy version and so on, the cost is roughly proportional to the size of the launch vehicle. So if NASA gives you a certain budget, a lot of that budget goes to the launch vehicle. You'd like to use a smaller one as you can. Another important feature is to be able to, when you optimize, you can trade fuel that you might otherwise have to use for scientific payload. And the scientists, of course, would like to increase the scientific payload. Or you can use that fuel, rather than using it for the interplanetary trajectory, you can save it for using it in maneuvers around Jupiter or around Saturn. and extend the spacecraft lifetime. So either way, if you can use less fuel for the interplanetary trajectory, you can have a better scientific return or a longer lifetime. So the types of interplanetary trajectories, roughly in order of difficulty: very easy to find impulsive, meaning high thrust chemical propulsion transfer with just 2 impulses. That could be, for example, an Earth to Mars Hohmann transfer. Even impulsive transfer with 3 or a small number more impulses is not too difficult to solve for. But then a considerably more difficult case is that of low thrust, sometimes called continuous thrust electric propulsion transfer. That would be exemplified by a spacecraft like NEAR, Deep Space One, which in fact in 1998 was the first one to use that technology, or the Dawn spacecraft. I'm sure you're familiar with all those missions. When we say low thrust, we mean really, really low thrust. You're probably aware that something like the Space Shuttle main engine has a thrust that's measured at around 250,000 pounds of thrust. Well, the electric thrusters, like the one on NEAR, the thrust is measured in ounces. But when you're in field-free space, remember that delta V equals A acceleration times delta T. So even though the acceleration is very small, it's down to maybe 10 to the minus 5 G, the burn time compared to the space shuttle, instead of maybe 10 to the second seconds, goes to 10 to the 5th or 10 to the 6th. So the product of acceleration times time gets you to roughly the same final velocity as the larger thrust engine. And then finally, the most difficult case to consider, well, maybe I shouldn't say most difficult. The most difficult we've done so far is impulsive chemical rocket transfer using gravity assist maneuvers and possibly some mid-course impulses. I could add what would be the very most difficult case, which would be low thrust transfer combined with gravity assist maneuvers, but I don't know of any that we've done so far. So impulsive thrust missions are relatively simple to solve because they're just parameter optimization problems. So you need to know the launch and arrival dates, the delta V at launch, and the delta V at arrival. If you're going to use more than 2 impulses, then you have to find out where and when to do the mid-course impulse. That adds a little bit of complication. On the other hand, if you're going to use gravity assist maneuvers, then it becomes much more complicated. Then the number of flybys, the planets you're going to use for flybys, the date of spacecraft launch, the dates of the flybys, the altitudes of the flybys, the dates and timing of, or the timing of and direction and magnitude of possible mid-course impulses, the date of arrival at the target, all those things have to be found. And then that becomes a quite complicated parameter optimization problem. On the other hand, low thrust missions are continuous optimization problems. They usually only have a small number of discrete parameters, such as the launch date and the arrival date. And then in between, you need to find a continuous history for things like the throttling parameter, meaning the thrust that you're using, and the thrust pointing angle. So here's the simplest case. And many of you have probably seen this in elementary physics, or maybe you've taken an orbital mechanics course. Hohmann transfer. Why is that relevant? Well, it's relevant because most of the planets that we go to are in nearly circular orbits, Mars being a bit of an exception. But even there, you can use something that's like a Hohmann transfer. So I've shown the Hohmann transfer in this left cartoon. going from a circular to circular orbit. The transfer orbit has a periapsis at the initial radius and apoapsis at the final radius. The velocities are parallel to the existing velocity. It's very easy to calculate the two delta V's with this formula. Now, this is for a coplanar case. Even if it's a three-dimensional case with inclination changes at each of the two berms, that's still very easy to solve. It just becomes there's a vector triangle, and you have to find the third side using the cosine law. It's still very easy. What I call a Hohmann-like impulsive transfer is this one on the right-hand side. This actually has a name. This is called the bielliptic. It's a three-impulse transfer. This can actually be optimizing in some circumstances, especially if there's a very large inclination change to be done, because that inclination change is almost exclusively done out at this distant point where the velocity is small, because the spacecraft has traded kinetic energy for it's traded kinetic energy for potential energy. So a inclination change, plane change maneuver is very cheap out here. And that can make this kind of transfer optimizing. If you, let me just say, so the Hohmann is easy to calculate. And in fact, there are three spacecraft that are almost at Mars, going to be there within the next week, that have used Hohmann transfer. And of course, the Hohmann transfer requires that the target planet, let's say in this case Mars, has to be at a particular point on its orbit here, outer orbit, at the instant that you leave the Earth, so that as the spacecraft moves toward Mars, Mars is going to meet it at this point. That lead angle is about 44 degrees by which Mars has to lead Earth. And that occurs every 26 months. And so if you look at the history of Mars missions, you'll see that they take advantage of the Hohmann transfer and launch about every 26 months. And a back of the envelope kind of calculation of the delta V required will probably get you within a couple of percent of the actual delta V. Of course, it's ignoring things like the gravity of other planets, solar radiation pressure, and so on. But those are relatively small, and it's reasonable to assume that the spacecraft is moving on a Keplerian ellipse. So you can do a very good back of the envelope calculation of the velocity change required. If you aren't able to do a Hohmann transfer, that is to say a transfer through 180 degrees, there's still an analytical solution. Suppose that point P1 here is the position of Earth at departure. P2 will be the position of Mars when you want to arrive. So you know the radius vectors, you know this interior angle, and so on. If you choose a desired flight time, which of course you have to know if you are going to determine where the planets are at launch and arrival, if you choose the flight time, then the problem is to find a section of an ellipse that joins these 2 points in the required flight time. That's referred to as Lambert's problem. And there's that can be solved analytically, even if you have plane change maneuvers as part of it. And it's very well described in this textbook that Siegfried mentioned that one of my colleagues and I wrote. It's called Orbital Mechanics. Okay, so the impulsive cases are relatively straightforward. What about the low thrust case? Well, that's a qualitatively different problem. We can no longer assume that the spacecraft is on a Keplerian elliptical trajectory. It is at any instant, but the precise ellipse is always changing because of the thrust. So in two-dimensional polar coordinates, here are the system differential equations. Notice that the thrust comes in on the right-hand side of these two equations. Beta is the thrust pointing angle that you can see here. beta would be 0 if the radial component of the thrust is 0. A is the maximum available acceleration, and S is a throttling parameter that simply is a number between 0 and 1. Now notice the fifth equation. This is the time rate of change of the maximum possible acceleration. And the reason that that is in there is because that acceleration increases as fuel is consumed. An equation for d mass dt would do just as well. So how do we find a minimum fuel trajectory for a system governed by that set of first order ODEs? Well, that was figured out 200 years ago by very eminent mathematicians. Let's let this quantity X, doesn't look like a vector, but let's let it represent that 5-element state vector that you saw on the previous slide. Let U represent a vector of the control variables, in this case, the thrust pointing angle, so it's a scalar. And suppose that we have a set of Q constraints that are functions of the states at the final time and possibly the final time itself. These could be as simple as saying that the position and velocity, the R theta, VR, and V theta of the spacecraft need to be equal to that of Mars at the final time, whatever that final time is. So you might have 4 simple constraints. So we want to find the control time history that minimizes this function. This is the usual choice for the cost function. It combines a function of the final states and the final time, this quantity capital T, with an integrated history of the states and the controls from the beginning to the end of the trajectory. So the necessary conditions for a minimum of J are the calculus of variations necessary conditions referred to as the Euler-Lagrange equations. We define what's called the Hamiltonian, which is the integrand of the cost function, plus the right-hand side of the, in this case, 5 system differential equations adjoined through a set of costate variables, this vector lambda. They're called costate variables or continuous Lagrange multiplier variables. I'm sure you're at least familiar with Lagrange multipliers for the discrete case. Here they're continuous variables. And so the necessary conditions become, of course, these 2 conditions, this satisfaction of the differential equations of motion, the terminal constraint equations. Then we have to add differential equations for the costate parameters, and these are equal in number to the original state variables. Terminal conditions for the costate variables, which also introduce another set of discrete Lagrange multipliers, the nus. Then what's called the optimality condition, that the partial of the Hamiltonian with the control variables has to be equal to 0. And then either the final time is specified, or you can add this scalar equation that has to be satisfied at the final time and allows you to find out what the optimal final time is. So notice what we've done. We've taken a system of what was originally 5 ordinary differential equations, and we've now made it a system of 10 ordinary differential equations. The original system has initial conditions specified. The new system has some of the initial conditions given at the starting time and other conditions given at the final time. So this is referred to, as you probably know, as a 2-point boundary value problem. Now, another complication is that we often can't use this optimality condition dH du equal to 0 to solve for the optimal control. That happens in a number of circumstances. One is when the Hamiltonian is linear in U, and so this equation doesn't give you any useful information. But another case is if the optimality condition, even if it works, gives you a U that is not within the available bounds for you. And this happens all the time. For example, in the spacecraft case, if you want to minimize flight time, this would tell you to use infinite thrust. You don't have infinite thrust, you have an upper bound. So in that circumstance, we replace that condition with what's called the Pontryagin minimum principle, which says that the instantaneous value of the optimal control is the one that instantaneously minimizes the Hamiltonian over all possible values of U. Somebody at the front door, that's the dachshund. Okay, so just to give you an example, for this particular relatively simple problem, the differential equations for the co-state variables. Stop it. Thank you. Okay. Sorry, Amazon delivery, and the dog went nuts. Okay. In this case, the differential equations for the co-state variables are given by this equation, and the F matrix that you see in there is this. So you can see that the differential equations for the co-states are linear in the co-state variables, but nonlinear in the states. So we've significantly complicated the problem, but there's no way to avoid that. Now, as far as possible objectives, in the impulsive case, usually the easiest thing to do is to maximize the vehicle final mass, which means that you minimize the propellant used. Come here. So to do that, we want to minimize the negative of the final mass, so you maximize the final mass. In the continuous thrust case, usually the easiest thing to do, the fuel minimizing trajectory, is to let the integrand, this capital L function, be the throttling parameter times the acceleration. So effectively integrating that over time, integrating the acceleration gives you the delta V. And remember the rocket equation, sometimes called the Tsiolkovsky equation, that says that the propellant mass required monotonically increases with the delta V. On the other hand, if you want to do a minimum time case, which sometimes arises, the person writing the equations can either choose to let this function of the final time simply be the final time, or you can let that phi function be 0 and let the integrand in the cost function simply be 1. So integral 1 dt is delta t. You get the same, you have to get the same solution either way. Now, let's write the Hamiltonian in a little more compact form by forming these vectors, one for position, one for velocity, one for co-states corresponding to the position coordinates, and one for co-states corresponding to the velocity coordinates, and let U be represented by the cosine and the sine of the thrust pointing angle. Then, if we use a minimum fuel case with this cost function that I showed you on the previous slide, then here's the new Hamiltonian. And if I rewrite that to isolate the throttle parameter, you get this expression. And now if I apply Pontryagin minimum principle to minimize H over all the possible U's, well, U appears in only one place, right there. So to minimize the Hamiltonian, what I do is I choose U to be in the opposite direction from the lambda V vector, which is this vector up here. That makes this as negative as possible. And one can show without much difficulty at all that what that implies then is that the optimal thrust pointing angle beta is the arctangent of the ratio of one of these co-state variables over the other, the lambda VR over the lambda V theta. So what's this mean? It means that if you can solve the 2-point boundary value problem, then this expression right here, you will then have lambda VR and lambda V theta known as functions of time from the starting time to the ending time. And so at any point in time, you can evaluate what the optimal thrust pointing angle is. Now, how about the throttling parameter? Well, this is just, if I let u be the negative of the lambda V, here's the Hamiltonian. And now the question is, what's the optimal value of the throttle parameter? Well, suppose we define what we call the switching function as the negative of this quantity that multiplies the throttle parameter. Then you can see that to minimize the Hamiltonian, what you want to do is you want to use maximum thrust if this quantity is positive, and no thrust if that quantity is negative. For this simple problem, this arises a lot. There is no case where intermediate thrust is minimizing. So the throttle is either fully open or fully closed. And in fact, an optimal control can consist of a sequence of alternating maximum thrust arcs and coast arcs. So that switching function can then be found as a function of time if we've solved the 2-point boundary value problem from the starting point to the ending point. So we get everything we need to know. The only problem is, what are the initial values of the Lagrange multipliers? So here's a simple example. This is one of the first ones that we solved this way a long time ago. So it's a typical problem. This is a minimum fuel, low thrust rendezvous. There's a spacecraft that's in this orbit at 1 AU, and we want to get out to 3 AU and rendezvous with a target that starts here. And it turns out that if you solve this problem using just the method I described, here's the optimal solution. There's a burn because the switch function is positive to this point, then it coasts, then there's a burn, then there's a longer coast, and then there's a final burn. And this is relatively straightforward to solve if you have a good 2-point boundary value problem solver. But this is a fairly simple problem. It's not even extremely challenging for a 2-point boundary value problem solver that's in MATLAB. Okay. So what's the difficulty of using this approach? Well, as you saw, it makes the system bigger. Instead of 5 differential equations, we have 10. I'm going to skip a couple of these. The other main problem is that every 2-point boundary value problem solver, some of you probably had experience with this, it needs it to be given an initial guess of the solution. And you may not have that. If you don't give it a good enough initial guess, it simply won't converge. Or if you could give it an initial guess, the other thing that can happen is it will converge to a solution that's in the neighborhood of the initial guess. Now, the difficulty with that is that many of these problems have lots of local minima, obviously only one global minimum, but the necessary conditions are entirely satisfied by the local minima. And you won't know that you have found a local minimum because there's no feedback to tell you that, oh, you only found the local minimum, there's a better minimum out there. Okay, so as an alternative to this problem of solving 2-point boundary value problems, in the early 1980s, a new method was found. It's called direct transcription solution. So the basic idea here is, in this cartoon, suppose this is just one state, could be the R quantity or the theta quantity. We assume that it has a certain continuous time history, and we discretize the time into n segments. There would be a similar cartoon for the other 4 state variables and a similar cartoon for the one control variable, the thrust pointing angle. Then the states at these discrete points become parameters in a nonlinear programming problem solver. but they're not arbitrary because they have to satisfy the system differential equations. So how do we arrange that? Well, there are lots of ways to do it, but consider this. What if we use just a simple Euler step? Then x2 is equal to x1 plus the value of the function evaluated at x1 times delta t. Well, that would be a very poor approximation for this case because f evaluated here looks like the slope at that point, and it would put you up here when you really want to be down here. But if you have a lot of segments between here and here, it would work. If it's just a small time, it would not be a bad approximation. Okay, so this becomes a nonlinear programming problem then. You want to minimize a certain function such as final time or the negative of the final mass. Putting in a whole bunch of constraints like this enforces satisfaction of the system differential equations. And you also can input upper and lower bounds on the states and the control variables. Here's an alternative that we came up with in about the late 1980s that I like a little better. It's qualitatively similar. This would be just one of the segments that you saw in the previous cartoon. What we use now, instead of a simple Euler step, is RK is the 4 steps of an RK parallel shooting. So suppose that the nonlinear programming solver thinks that one of the states has this value at the left-hand side of the segment, and you use these controls at these 3 points in the right-hand sides of the RK step formulas, and you propagate to here. Well, you get a value for the state, but let's not make it an NLP parameter. Let's just use that to initialize another RK step, and then do it again until you're all the way over here. Well, this value up here is what you get by using RK integration, but the NLP solver thinks that the value is this, so you have to have the NLP solver close that gap by forcing it equal to 0. And this actually works quite well. It has the virtue of minimizing the number of parameters that you need for the states, but using a lot more for the controls, which is generally a good thing. So this just describes the nonlinear program. You have a long vector of all the states and all the controls. You may, in addition, have some discrete parameters like a launch date, or if you're looking at solving a launch vehicle problem, maybe the staging times, an interplanetary trajectory problem, some discrete parameters could be flyby dates, etc. And so this is basically a nonlinear program. We have upper and lower bounds on the parameters themselves, the state variables, usually no linear bounds, but then the C of P is a collection of all the nonlinear constraints, and if they are this last step that closes the gap at the right-hand side, then the upper and lower bounds for that will be 0. And you can solve that kind of problem using, for example, fmincon in MATLAB. And we've solved problems with as many as 3,000 parameters. So you can do a fairly fine discretization of the time history. So that method would solve this problem I showed you earlier very, very easily. But it has limitations. You have to specify a priori what the form of the solution is going to be. So in this case, if you tell it that the solution is what it actually turned out to be, burn, coast, burn, coast, burn, you'd get this solution. But what if you don't know that? If you think that it's just going to be a burn, coast, burn, kind of like a low thrust Hohmann transfer, well, the solver would give you that. It would give you the optimal solution that has a burn, coast, burn structure, but it wouldn't give you any information that tells you you can do better if you add another burn and another coast. So you get what you asked for, which is a little bit of a problem. But you can avoid that in some cases by over specifying. For example, I could put an initial coast in here ahead. I could make it coast, burn, coast, burn, coast, burn, and then even add another coast and burn. And if they are not optimizing, they get collapsed as the NLP solver solves the problem. So you can over specify and then you would get the right answer. But the big problem down here is that just as with 2-point boundary value problem solvers, you need to give it a good initial guess in order for it to converge. And then you still have the same problem that the solution tends to be in the neighborhood of the initial guess that you give it. So you still have this problem of possibly converging to local minima when there's a better global minimum. Let me just give you a simple example of a complicated problem where you really have no idea of what a good initial guess would be and how to get around it. So this is a problem that that we solved on our way to solving a more complicated one. I'll show you a figure of that before. But let's suppose that we want to use low thrust to go from low Earth orbit and enter and then remain in a Lyapunov orbit, which is a 2D halo orbit, centered on the interior Lagrange point in the Earth-Moon system. Okay, so, but we have no idea what a good initial guess for that trajectory is. It's quite complicated, you can see, because it has many revolutions around Earth before you get escape energy. So the first step, let's assume that the thrust is always directed along the velocity vector. That maximizes the rate of increase of kinetic energy. Well, and then stop the integration when you get anywhere near the final orbit. Well, that gets you close, but it's not great. You do have to pick the right starting point, because if you don't, you'll end up going off to the left instead of off to the right. But that's trivial. But so we pick a good starting point, we get here. So then the next step is to use that as an initial guess for a second nonlinear program where we require to hit a specific point on the orbit, but still not necessarily the one that minimizes the fuel use. Then we take that red trajectory and use it as an initial guess for a third solution that not only arrives at a point on that trajectory, but has just the right velocity so that it would then follow that Lyapunov orbit. And then finally, we use that as an initial guess for a fourth solution that relaxes the location constraint and says, okay, now find an entry point anywhere on that orbit if it minimizes the fuel used. So you see now how you can start with absolutely no idea what a good initial guess is, and with a homotopy, you can still solve the problem, but it's a little time consuming. The real problem we wanted to solve was this one, which is a low thrust transfer from low Earth orbit to a low lunar orbit using invariant manifolds. You probably know about those. Those are coasting trajectories in the three-body problem. So we used a method very similar to the one I just showed you to find a trajectory that takes the vehicle and enters a halo orbit around the interior Lagrange point, then departs that orbit and goes to the moon. What looks like the moon there, this yellow thing, that's actually very, very close-knit spiral that goes down to a low lunar orbit. This is an extremely complicated problem. We actually used it as the cover art for the other book that that Siegfried mentioned on optimizing space trajectories. So if you're patient enough, you can get these direct methods to solve very complicated problems. Okay, well, in about the 1990s, people realized that it would be really nice to come up with a solution that is not prejudiced. That is to say, that doesn't require an initial guess of the solution. And methods that are initialized totally randomly are evolutionary algorithms, one that you probably all know is a genetic algorithm, or a heuristic like particle swarms or ant colony algorithms. Let me get rid of this sunlight here. So these are really nice because they don't require any a priori information about the solution. So you don't prejudice it to look in a certain neighborhood when you use these methods. Let me just say just a little bit about genetic algorithm if you're not familiar with it. The basic idea is to create chromosomes that are strings of numbers. It can be binary. This one is not binary, but it's the same idea. Suppose in this case, we have strings that are 8 elements long, and you create some large number of them, maybe 500 of them. And each one can be decoded to tell you something about the space mission, and it can be decoded and give you a cost. So for example, the first 3 numbers here could be the departure date following some given epoch date. The next 2 could be, let's say, the time that the astronauts are on the surface of the object, asteroid, or maybe even Mars. And then the third numbers could be these 3 numbers could represent the number of days after the stay that you arrive back on Earth. So that information is sufficient to solve the Lambert's problems to give you a delta V cost for the mission. So you generate, let's say, 500 of these strings randomly, and then you evaluate the cost of every one. Then let's say you throw away the worst 250. Initially, a lot of them are going to be terrible. A lot of them may, because they're random, they may have departure dates from the asteroid prior to the departure from the Earth. So they make no sense. So you give them a ridiculously high cost, like $1 million, and then they'll remove themselves. So you remove the high cost ones, you take the remaining ones and choose them at random to become parents for an offspring. You select pieces of the parents to create, in a random way, to create children. And then in a very small number, usually around 0.5%, you just flip 1 digit randomly. And then the process repeats. And as the process iterates, the solutions generally get better and better. You can run it until you reach a certain goal, or you can just run it for an arbitrary number of generations. Particle swarm is qualitatively different because it's not an evolutionary technique. In this case, every individual particle is trying to improve his or her cost. They're trying to improve themselves. But the initial population is still randomly generated. So every particle is initially inserted in an n-dimensional space. Then the coordinates of the position are used to evaluate the cost in exactly the same way that it was done with the genetic algorithm. It's decoded and a cost is arrived at. A global best particle is identified. And then in the next step, or in each successive step, the particles move in this n-dimensional search space. They take a step, it's referred to as the velocity, but it's really a displacement. They move with a vector that's the sum of 3, it's a linear combination of 3 vectors. The first is the so-called inertial component, which means take a step in the direction that you were moving at the last step. The second step is called the cognitive component, which says move towards the best position that you personally have ever experienced. Now that's in there because it's possible in this method for a particle to move away from, or to move to a new position that's worse than the position that it was in. So this one's saying, take me back to where I was because it was better. And then the third one, which is the most important, is the social component, which says, take me towards the particle that has found the global best location. Now, each of these 3 vector components is multiplied by a random number between 0 and 1. So it's quite stochastic. Because the initial population is randomly generated, and because each of these components is multiplied by a random number, you can run the PSO and you never, of course, get the same result twice. And then you repeat the process for a fixed number of iterations or until you don't see any more improvement. Here's a simple example. Shoot. Oh, well, for some reason. Well, I've lost the animation. The object here is to minimize a simple function of 2 parameters subject to constraints. Now, I didn't really say much about constraints. There's no native way to handle constraints in these heuristic and evolutionary methods, except to add them as penalty parameters. So you add the constraints to the function you want to minimize, and through weights here called C1 and C2, and then the optimizer can minimize it if it drives the constraints to 0. So in this case, we're trying to minimize this function subject to the requirement that the particle, that the solution lie on this straight line and that it be on the interior of the ellipse that's given by this equation. And unfortunately, up to now, it was working, but it no longer, maybe it's because, yeah, maybe it's because it doesn't realize it's a, turn that off. Let me, here we go. It didn't like it being a laser pointer. Okay, so here are the particles moving in a 2-dimensional space, and you see that they very quickly converge on the optimal point. Okay. Well, I'm really just going to talk about the advantages. It's really easy to code. Extremely easy to code. You don't need to know anything about optimal control theory. You don't need to know about Euler-Lagrange equations. A high school kid could do this. But the most important thing is that you don't have to prejudice it with any kind of initial guess. Also, if you use a large enough search space and a large number of particles, you're more likely than the other methods to find the global minimum, because they do a very efficient search of the space. And if it doesn't find it on the first try, you never are satisfied with doing it once. You run this thing multiple times, and then you can be fairly confident that you found the global minimum. In fact, it's funny, if you watch these things iterate, their animations on the web, it looks like a swarm of birds going after some kind of prey. You'll see the particles all head for a point, which turns out to be a local minimum. And then one of the particles will find a lower cost, and then the entire swarm will turn and head towards that point. It's quite fun to watch. Of course, once you get above 3 dimensions, you can't watch it anymore. So here's a simple example. The one main disadvantage is that you have to parameterize it with a small number of parameters. I mentioned that for the direct transcription solutions, you can have thousands. We've solved problems with 3,000, 4,000 parameters. Here you have to use typically less than 100. So you have to find some way to enable the problem you want to solve to be described by a small number of variables. So here's an example one of my students did for a master's thesis. It was to minimize delta V for an asteroid sample return mission, with the astronauts staying between 8 and 25 days at the asteroid and returning to Earth within 1 year. And we searched the near-Earth asteroid catalog for asteroids that would satisfy the following criteria. You can just read that. And it turns out that people at NASA had done this. We found a paper where they'd done this, but they had to generate on the order of 10 to the 5th missions for each asteroid, because they looked at an astoundingly large number of possible dates for the Earth departure, the asteroid interception, then the asteroid departure or the stay time, and the Earth arrival. So there are only 4 parameters, but if you have a wide range of values for those, you have to do on the order of 10 to the 5th missions. It's a brute force approach. We decided to do it with the particle swarm. And here is just one page from her. She had like 10 pages of results. I won't go through a lot of them, but just to give you an idea, you probably are all familiar with Apophis, which is not just a near-Earth asteroid, but a potentially hazardous one. But this shows 2 different possible flights found by the particle swarm. And this is done in hours on a laptop for all of them together. It finds an optimal launch date. It finds an optimal time for the outbound flight, an optimal stay time at the asteroid, and then the total mission duration, so which effectively gives you the return trip time. And we did this for quite a few asteroids, and it found very good solutions, much easier than what the people at NASA had done with a brute force approach. Notice that some of them bump up right against the limits. The upper limit for the stay was 25 days. The upper limit for the mission duration was 365 days, but not all of them. Here's one that's not close to either upper limit. When you're an optimization person and you see the upper limits being bumped up against like this, what it's telling you is that if you could relax them, you'd do even better. But we took the same numbers that the NASA people used. Here's another example. I won't go into a lot of the detail. It's a maximum radius orbit transfer for a solar sail. So this is continuous propulsion, but not electric. And the idea was to find the solar sail orientation angle, this angle alpha in the differential equations, that allowed a transfer from 1 AU, a circular orbit at 1 AU, to the largest possible circular orbit in a fixed time of 450 days. And the way he cleverly parameterized this was to describe that time history alpha as a sum of 7 quadratic splines with coefficients given by these quantities alpha 1 through alpha 7. And the PSO found the optimal values of those 7 parameters. It also actually, I say quadratic splines, but in fact, the optimizer was also given a choice of splines and found that the best ones were quadratic. So it actually chose quadratic. It chose this number 2 instead of 1 or 3. And here's the result for the time history of the orientation angle of the solar sail. The PSO is the blue. We then use that as an initial guess for a direct transcription method, as I described earlier. And that's the dotted line. You can see they're almost on top of each other. It did a really, really good job of finding a solution. So it used just a handful of parameters, about 8, whereas the direct transcription solution needed thousands. And this is also faster. Okay, so now let me conclude with the most challenging problem for mission planners. The interplanetary trajectory with gravity assist maneuvers. This is the Galileo or Cassini trajectory problem. This is a difficult problem, even if you assume impulsive chemical thrust, which is what they use, not low thrust. It's difficult because there are so many free parameters. The date of departure, the RA and declination of the departure velocity vector, which planets to use for flybys and in what sequence, what will be the dates of the flybys, what will be the altitude of each flyby, what will be the optimal date of arrival at the target planet, and then the dates, the magnitudes, and the directions of any, I say usually small mid-course impulses. I say usually small because at this point in the trajectory, the vehicle is no longer connected to an upper stage of the launch vehicle. So any fuel it uses is fuel that it can't use for extending its lifetime at Jupiter, for example. So you really want to minimize that. It'd be nice to have a trajectory that doesn't need any mid-course impulses, but sometimes small ones are required just to help set up the one flyby for the next flyby. Designing trajectories for Galileo and Cassini was a many person year effort. I know a lot of the people who worked on it, and it was a big problem, aided of course by their experience as orbital mechanicians. They were able to rule out a lot of possibilities because they just don't make any sense. This is referred to in control theory as a hybrid optimal control problem. That is to say, there are a number of discrete parameters that the solution depends on, and then there are continuous parameters like the radius, the azimuthal angle, in the earlier terms, the r, the theta, the v sub r, the v sub theta, and so on. The way we chose to solve the problem is really pretty much the only way you can approach these hybrid optimal control problems, which is to divide the problem into an outer loop and an inner loop. In our case, we use the outer loop to define the identities and the sequence of the planets to be used for the flybys. The inner loop is then called by the outer loop, and it says, okay, you're going to use these planets in this sequence, assuming that what is the optimal trajectory? Find me all those other things, the dates of departure, the date of each flyby, the altitude of each flyby, etc., in order to satisfy the mission constraints that you've given me. Then the inner loop returns the cost of that trajectory, if it's at all feasible, back to the outer loop. So that inner loop problem is a conventional optimal control problem. You can solve it with the methods that I've described. You could set it up as transcribe it into a nonlinear programming problem, or in this case, we actually used another heuristic that I didn't describe. It's too messy to describe in detail here, called differential evolution. But it's just another evolutionary algorithm. So one of my PhD students then tried to automate this mission planning process, basically to automate what was done by the people at JPL for Galileo and Cassini. And he actually relied on work of two previous PhD students. It was really an effort that took place over a decade. They had each made advances that allowed Jacob to actually complete the goal. So we wanted to create an automaton that would solve this complicated mission planning problem with almost no a priori information provided. Simply a range of dates that are allowable for departure from Earth and allowable for arrival at the target planet. Then, of course, you do have to give it information about what launch vehicle is being used so that you know what your velocity, hyperbolic excess velocity will be when you leave the Earth. You need to provide a little bit of information about the onboard propulsion, so you know how much fuel would be consumed in a mid-course impulse, just basic stuff like that. But no, you don't have to supply any information, any instinct as to what the solution will look like. With regard to the outer loop solver, we used a genetic algorithm. And the easiest thing with the genetic algorithm is to use a base 2 number for the length of the chromosome. So either 4, 8, or 16 parameters or numbers. We needed to use 16, but there are only 8 possible planets that we could use for flybys. So the student came up with this concept of using null genes, meaning that a GA string like this, 2, 9, 3, 10, 12, 3, 11, 14, would decode to Venus, which is body 2. The 9 is a null code, there's no planet. Then 3 is Earth, Then 10 and 12 don't correspond to any real planets. 3 is Earth again, and 11, 14 are both non-existent planets. So when you decode it, you get Venus, Earth, Earth, and some null planets. You remove those and you prefix the starting body, append the destination body, and there's your sequence. Earth, Venus, Earth, Earth, or depart Earth, Venus flyby, Earth flyby, another Earth flyby, arrive at Jupiter. Then the inner loop solver, I'm kind of running out of time here, so I won't go into a lot of description about it, but I described a Lambert problem, which looks like this. So if the date for a flyby is known, you know where the position of the flyby planet is. If the date for the next flyby is known, you know where that planet will be. You then know this interior angle and the lengths of those radius vectors, and you know the transfer time, so you can find the elliptic arc that connects them. So the individual problems going from one planet to the next are Lambert problems. They're relatively easy to solve. The only complication is that the required velocity change from the flyby and the turn angle to set you off in the right direction to go to the next flyby planet might require a flyby that's below the planet's surface, which isn't going to work. So we have to put in a requirement that the flyby altitude be above the surface of the planet in order for it to be feasible. Ones that don't satisfy that are eliminated as trajectories that have a ridiculously high cost. Then we also allow one mid-course maneuver on each leg. So here's a cartoon showing the basic idea. The optimizer is choosing the launch date, and then for each phase, the flight time, which gives the arrival date at the next planet, and so on. A so-called burn index, which is a number between 0 and 1 that tells you how much of the leg is used before you do the mid-course impulse. Most of the time, the mid-course impulses turn out to be 0 or negligibly small. The so-called B-plane insertion angle at the arrival planet, I don't have time to go into detail about that. And the flyby periapse distance ratio, which has to be bigger than 1, otherwise you tunnel into the planet.
So sorry to interrupt you, Bruce, for just 1 second. So we are on top of the hour. So thanks everybody who has to jump ship. Thanks for attending, and for everybody who can stay around a little longer. I'm happy. I think Bruce is happy to have some questions.
It's getting very close to the end.
Thank you.
So here's the actual trajectory for Cassini. Once we had this automaton written, we wanted to test it against an existing solution. And we knew that this Cassini trajectory had been tested multiple times. The JPL people did indeed find the best solution. And so you can see here's launch in October 1997. Then there is a first Venus swing by in April of 98. Then it goes around, there's one mid-course maneuver in December of 1998. Then it comes around again, there's a Venus swing by in August of 99. And then the spacecraft is on its way to a Jupiter swing by. And then that took it to Saturn. So we were hoping to see if our automaton could reproduce this with, as I said, almost no a priori information. So here is what we told it. We told it the desired capture orbit radius, the desired capture orbit eccentricity, which all corresponded to the actual parameters, a launch window open date in April of 97, a close date in January of 2000, so a little more than 2 years open window, upper bound of flight time of 10 years, and then a maximum of 8 possible flybys. Of course, we knew the answer was that there were only 3, but we didn't use that. And here is what the optimizer came up with. It finds the optimal solution, Venus, Earth, Jupiter flybys. with a cost of just a little over 1 kilometer per second. These are the next 20 best solutions that the optimizer came up with. All of them are pretty bad. Even the next best one uses more than twice as much fuel. Here's what this is our solution, but it really is the same one that you saw in the JPL cartoon, except this one's harder to visualize. Here's our result. Compared to this is our automaton solution versus the actual Cassini mission. The launch date that our optimizer comes up with is within a week of the actual. The first Venus flyby is also within about a week of the actual. The second Venus flyby is just 1 day different from the actual. The Earth flyby is also just 1 day different from the actual. The Jupiter flyby, however, is almost 2 weeks different, and the Saturn orbit insertion is substantially different. There's a reason for this. It's not the fault of our optimizer. The actual Cassini mission had a suboptimal requirement that when it arrived at Saturn, it did a close flyby of one of the moons. I think it was Titan, which was not necessary to minimizing the propellant use, but it had a scientific purpose. But we didn't include that in our analysis. So up to that point of the Jupiter flyby, things are pretty close. And then the Saturn orbit insertion is different because we didn't include that constraint. Our solution has a slightly better cost because, again, if you add some extraneous requirement like needing to do a close flyby of one of the moons as you're inbound, that's going to make the cost higher than if your only objective is to minimize fuel. So in summary, just in my career, there's been a dramatic improvement in the methods that are available for solving optimal trajectory problems of any type, not just interplanetary transfers. The direct methods are generally much better to the calculus of variations-based methods because they're just more robust than solving a 2-point boundary value problem. Since about 1990, we've now found that heuristic algorithms and evolutionary algorithms either can be used alone if you're clever enough to reduce the number of parameters to a pretty small number, or you can use them, as you saw in this last example, synergistically with the direct transcription methods. And the advantage of that is that the synergistic combination allows the evolutionary algorithm or the heuristic to do a better exploration of the solution space, and it's not prejudiced by any kind of initial guess. So I described this automaton we came up with. What I didn't mention is that it works in just a few hours on a laptop, and it replaces many person years of effort that were required at JPL to do Cassini and Galileo before that. And if anyone has any interest, this solver, NASA was clever enough to give this PhD student a scholarship. Forgotten what the name was now. It's changed now. But he had a 3-year full ride scholarship from them. And they then hired him on, and he took the software with him. They paid for it. And it's now become the EMTG, or Evolutionary Mission Trajectory Generator, which is the software that NASA Goddard now uses for all of its mission planning. It's been improved because he's had 6 years now to work on it, but you can download it for free from the NASA Goddard Space Flight Center website. I would mention, however, it's not what you call easy to use, but it's free. And if you work hard enough or put a PhD student on it, they will eventually get a solution with it. And that's what I have to say.
Thank you so much. Thanks, Bruce. If you want, you can unmute and clap. And since you are all still here, I imagine you have some more time for questions. And maybe Bruce, it's your break, so I don't know if you're willing to answer a few.
It's fine. I'd be happy to answer any questions.
Sounds good. So what I would say is either raise your hand, or if you're quick enough, unmute and ask a question, please. I don't see any hands raised. So, oh yeah, Danilo, please go ahead.
Thank you so much for your talk. It was very interesting. I have two questions. First, I was wondering for your results about using the evolutionary algorithm for the trajectory to Saturn. That several week or month discrepancy that you saw at the end, did you try including the moon flyby, and did that close the gap, or you didn't try that?
No, we didn't try it. We were pretty happy with what we got, and that's actually a fairly difficult constraint to put into the problem.
I see. And the second question is, I know direct methods for things like low thrust trajectories have been criticized for the numerical issues dealing with the very small numbers involved and the differences in magnitudes of variables. Have you had issues with them? And off the top of your head, what are some best practices that you've used?
No, we haven't really had much problem. What you generally want to do with these kinds of problems, the NLP solvers are much happier if everything is roughly about the same order of magnitude. Mm-hmm. So if you try and work in kilometers and days and so on, that's really bad. So what we always do is we work in normalized variables. So the distance unit is always 1 AU, and the time unit is that 1 year becomes pi time units. Mm-hmm. And of course, the angle variable is trivial because it's just going between 0 and 2 pi. So if you do that, everything is scaled except for the thrust acceleration. Everything is scaled to about order 10 to the 0 or 10 to the 1. Mm-hmm. And that's if you solve it, almost any kind of nonlinear programming problem, you find that that's what they pretty much always suggest, is to transcribe the problem so that everything's roughly the same size.
Mm-hmm. Okay, thank you very much, and thanks for your work.
Thanks. Then we have Kyle.
Hi. Yes, I had a question about actually implementing these orbits. So when you actually try to go run this, how accurately can you actually reproduce the trajectories that you've come up with in these simulations? And do you have to worry about if this trajectory gets slightly off, how that'll propagate down the line?
I'm not sure if you're talking about solving the trajectory or actually flying it.
Actually flying it. Let's say you burn, or you end up going slightly faster than you anticipated or something like that. Is that an issue that you run into?
Well, not personally and not in my research, but if you look at how JPL implements a flight, they're of course tracking the spacecraft, as let's say this recent one that's on its way to Mars. They're tracking the flight, and they have built-in opportunities during the flight for doing course corrections. And so they will examine the trajectory, and if it starts to depart slightly from the desired trajectory, they will do course corrections at their specified times. And in many cases, the trajectory is so close to the predicted one that they can simply bypass some of the anticipated course corrections. Or even when they do them, they're trivially small, like a handful of meters per second. So I guess what you could say is that they've developed the technology to a very high degree, which of course you have to do if you're going to have a hope of landing, let's say, a rover within a couple kilometer circle on Mars. You have to know where it is en route to that same accuracy. You have to know the location of that arrival point on Mars in the solar system to that kind of accuracy too, right? So it's really incredible that the whole thing works as well as it does.
Don't jinx it, Bruce.
Thanks. Yeah, very interesting.
Okay, thank you, Kyle. There's one more question, and then I think we'll let Bruce have a quick break. Wes, please.
Yes, sir. Thank you for your talk. And I just wanted to ask kind of a big picture question of where do you think this field is going? As in, like, what sort of questions are being worked on right now, and what sort of problems do you see kind of on the horizon for your field?
Wow. That's hard to say. When I started, the available solvers, as I kind of alluded to at the beginning, were not very good. And they were challenging to work with because you had to solve 2-point boundary value problems. In fact, one of my PhD student colleagues at Stanford, working with the same advisor, he wrote his entire thesis, and there's a long paper in the J Guidance, Control, and Dynamics. He wrote his entire thesis on a method for coming up with the initial Lagrange multipliers to solve that 2-point boundary value problem for a low thrust transfer. Mm-hmm. So that was how complicated it was. Now you could almost say that it's relatively easy. So where is it going to go? I think this method is going to be applied to more and more complicated problems. You're probably aware that one of the more challenging problems now in the last 10 or 15 years is leveraging these so-called invariant manifolds, which are these coasting trajectories in the 3-body problem.
Okay.
That allow a spacecraft to go from one point to another in either Earth-Moon space or even in the solar system without using any propellant whatsoever. You can actually transfer from one invariant manifold to another. Let me see if I can zip back here to the right slide, this cartoon here.
Right.
See if that's up. So this kind of thing. This is an Earth-Moon trajectory using invariant manifolds. And when the yellow disappears, it's not thrusting anymore. It's on one of these invariant manifolds. And it doesn't look like it because this cartoon is in a system that's rotating with the Earth-Moon system. But you can kind of see it here, this thing that looks like a fishnet stocking. These are possible invariant manifolds, meaning coasting trajectories that would allow a spacecraft to go when the thrust is cut off and arrive and even enter this halo orbit about the interior Lagrange point. And then with a trivial delta V, like just 1 or 2 meters per second, you can hop off of that and get on a trajectory that goes to the moon with no further effort. It actually goes close to the moon. So you can't use these for manned missions because they take way too much time. Mm-hmm. But if you simply want to send like supplies to a lunar base, you could do this. So this is a very active field, using this kind of trajectory optimization to do these trajectories that use both thrust and invariant manifolds to get places with very low cost compared to the way that we did it, say, during Apollo, or that's envisioned for the upcoming Artemis mission.
Yes, sir.
That's probably the most dynamic application for this kind of work that's going on right now. That's the most challenging problem that there is right now.
Sure. Well, thank you.
Sure.
All right. Thank you very much. I think we'll leave at least 5 minutes for Bruce to take a breath before he is meeting with James. Thank you so much, everybody, for coming. If you have any more questions, I'm sure Bruce will be happy to answer them through email. If you ping me personally, I'll ask Bruce if I can share his email address with you. So thanks again. For coming.
Yeah, you're welcome to share it. Stephen has it also.
Okay, excellent. Thank you very much, everybody. And yeah, we'll see you with the next visitor in, I think, a couple of weeks. Thanks.
Bye, everybody.